Okay, so here we go. So last time we were talking about doing integrals in spherical coordinates, and so picking up where we left off, another example in spherical coordinates. We're going to look at this ball right here. So so this ball right here, whenever y'all are ready. Okay, all right, so here we go. Okay, all right, so this ball right here is our domain, and we're going to think about how to slice this up in spherical coordinates. Remember, we're always going to do our differentials in this order. Are we all good? Okay. All right. Okay. So theta first. Remember, we always use this order. This is always, asterisk, rare exceptions, I suppose, but always use this order, practically speaking. And so theta slices first. Here's what theta slice looks like, and here's where having a good picture really becomes essential. You have to think about how do these slices, theta slices, how do they intersect with our solid that's given? Right. So this solid, you really need to have the picture to recognize that the entire solid, right, is on the, what you might call the positive side of the xz plane, the positive y side of the xz plane. Right? There's nothing over there on the negative y side. So the range of values then here is, let's see here. So the first one, the first theta slice is going to be about like this, right? And then theta, these theta slices will kind of move around like that, constantly taking out these cuts, right? These kind of, now those cuts will be sort of discs like that, and it's going to finish the very last one way over here on the sort of the back side there, sort of the negative x side of the xz plane. That'll be our last slice, which of course is where theta is pi. Right? So I think this is the hardest part of this problem, is being able to have a sufficiently good picture and a sufficiently good sort of geometric visualization of what these slices look like, right? To be able to figure out these outside bounds. And everything else is kind of, I'm going to say, business as usual. I mean, if you look at one of these theta slices, here it is, again, drawn looking straight on at it. Here's what it looks like that. And not too big of a challenge to see that these phi slices start going straight up, right? And they kind of go around. And then the last ones, they get shorter and shorter as you get closer and closer to pi, and they don't actually disappear until you get to pi. Right. Okay. So the rest is, I'm going to say, familiar details and all stuff that we've talked through analogous stuff before. But I do think this example is really good for just to see that there is this sort of geometric challenge that you just can't get around in finding the theta bounds. Okay. All right, the last example I want to show y'all is mostly about drawing, frankly. So again, theta slices and phi slices and rho slices, and you got to find the equation of this or that. That's all familiar and stuff that we've talked about. Let me talk through why this is a difficult artistic challenge and what you can do to work around it. So we have this ball here. That's that ball. And so we're looking at points that are inside of that ball. But now, very importantly, we want, you'll see this is a greater than or equal, not a less than or equal. So here, this says we're looking at points that are outside of this red ball. All right, so you're going to take the purple ball and then exclude every part of the purple ball that is also in the red ball. So this is an example, kitchen metaphor. If you had like a ball of something, it's like you got a melon baller and you just or an ice cream scoop, right? You take an ice cream scoop right out of the underside of it. And what makes this hard to think about geometrically is that if you ask, okay, well, like I could take a whack at drawing this thing. Let's kind of sort of like this or something. That's what my domain is. Well, the problem is there's really more going on than this. This makes it look like there's a corner right there, but there isn't. There's no corner there. And so, well, okay, how do these spheres intersect? You could probably persuade yourself that there's kind of an edge right there. Right? So how do I sort of color this in? I mean, if I were to sort of color in sort of the whole thing, it kind of makes it look like it has a flat bottom, but it doesn't. Right? It's got a scoop taken out of the underside. If I'm looking sort of right through there, I hit some solid there, but then I hit the air gap underneath it that's been scooped out. And then I hit more solid on kind of the back side. It's a weird thing to draw a reasonably good picture of. And when things are hard to draw, they're also hard to visualize. And when they're hard to visualize, they're really hard to talk about cross sections. So it would seem like a difficult geometric / intuitive / artistic challenge to draw a cross section of this. So let me tell you my workaround here. So it's a neat observation to make. I don't really have to visualize the whole actual solid. Right? What I can do is recognize that this solid is made up out of other simpler things. And so going back to what we saw before, there is, to begin with, this ball. Nice and simple. It's just a ball. And if I ask the question, what is its cross section in a theta plane, a theta half plane, if I take a theta slice out of this ball, hey, no problem. Nothing to it. It's just a ball. I'm just taking a cross section with a half plane, and I'm going to get, as you see over here, looking at one of my theta slices, I'm just going to get this half a disk. Right, like that. That was easy. Right, now let's go back up to here, and what else do I need to be concerned about? Well, let's see, apparently I need to be concerned about this ball. Now, how the red ball interacts with the green ball, we'll worry about that in a minute. Let's focus for just a second on what is the cross-section of that red ball in the same blue theta slice. And again, it's a ball. We're cutting a little slice through it, nothing to it. It's just going to be another half a disk. Right? So what makes it easier to deal with is now that I have the cross sections of each individual piece, now I can ask, okay, what happens, no, not in this context, what's in green but not in red, right? But in this context, what is it that's in the green but not in the red? No problem, I'm looking right at it. In the green but not the red is that thing right there that I have highlighted in gray and then I'm trying to color yellow. So that's what our theta slice looks like. So again, I think it's much easier to take this approach. Don't try to slice up a complicated solid if you don't have to. Instead, if it's made up out of simpler components, slice up the simpler components and then look at these slices to think about what you're actually interested in. Okay, so again, now everything that proceeds from here is kind of what I'll call details. So for example, the range of values of phi, well, here's what a phi slice looks like. First one is here at 0. All right, last one is at this point. And let's see, getting rid of my distractions. What can I say about that point? Well, again, different approaches you could take, but it's pretty easy to notice once you see it anyway. This point, again, we have this advantage of a equilateral triangle right there, and so I immediately know that that value of phi is pi over 3 because, again, equilateral triangle. Everybody happy? Blah, 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 everything else is the same. Yeah?
If you don't know, if you don't see the equilateral triangle,
yeah,
just like set the two sphere equations.
Yep, that's exactly right. You would observe that this point that we're interested in is on this sphere, which has this equation, which again, you got to do some work to get to that. And then it's also on this sphere that has, well, conveniently that equation. And so, yeah, the other sort of alternative way to find this value is to set this equal to that and solve. Yeah. Yes?
Can you go over again how do you figure out x is equilateral?
I'm sorry, I just can't hear you.
How do you figure out if this is a equilateral triangle?
Oh, yeah, sure, no problem. So this edge and this edge are radii of that disk, right? And then, let's see, let me get a contrasting color. This one is a radius of that disk. So all ones.
Oh, okay.
Yeah. Sure. Okay, so that's all I'm going to tell you all about spherical coordinates. And we're going to move on now to the last third or so, you might say, of 5.5. And I guess I should say of what I'm going to, my discussion of 5.5. So there's a really powerful application of change of variables that I believe that this book and most multivariable calculus books undersell. It's a really, really powerful computational tool. It's super convenient. I used this a bunch of times, countless times when I was an undergrad. It's just super useful. And y'all have seen the single variable version of this, which you see on the screen here looking at you. This is called the odd symmetry theorem. And here it is. The odd symmetry theorem says that if you are looking at an integral, and if the integrand is odd, here's what odd means. And if the domain, let's see here, color choices, I'll use dark blue. If the domain here is symmetric, now here's a definition of what we mean by symmetric. This is formalizing something that y'all don't need to formalize. Don't worry about this. You can look at it if you like. But symmetric means exactly what you think it means. It means that when you flip it over the origin, it's the same, right? So you might think of this interval here, the bounds for this integral, it just means like negative a to a. It means the lower bound is the negative of the upper bound. But better to think of it as that when you flip it over the origin, it doesn't change. When this happens, when both of these conditions are met, your integral is 0. You drop the pen, you walk away. You don't have to integrate anything. No antiderivatives. No substitutions or integration by parts or, God forbid, partial fractions or any of that nonsense, right? Just boop, 0. Awesome. Okay. Now, how often does this come up in single variable calculus? Well, you could argue maybe not super often, but here and there, and I suppose it's kind of convenient. We're going to talk about, I'm going to skip over this and come back to it momentarily. We're going to talk about a two-dimensional version of this. The two-dimensional version, a little bit different. We were talking about reflections over the origin, right? And here, we're going to broaden that to reflections over a line. And if you have a line, any line in the plane, any line at all, reflection just means exactly what you think it means, like that. Is that cool? So this is kind of, we can define oddness and symmetry of a domain with using sort of this in developing our sort of two-dimensional version of those ideas. So in particular, when you reflect, the value of the function should get a minus sign. That's oddness. And notice that this is, again, highly analogous to the idea of oddness that we had in a single variable context. Now, in this single variable, we only thought about reflecting over just the origin. Here, broader, right? Any line. Pick your favorite line, doesn't matter. More possible applications. Likewise, we can define what we mean by symmetric over the line. And again, it means exactly what you think it means. It means that if you flip it over the line, it doesn't change. It is its own reflection, right? And you could think of that as being sort of what this is saying, but if you aren't comfortable with what I mean by that, don't worry about it. It's fine. Okay. All right. So here is the two-dimensional version of odd symmetry. Notice I've written the theorem in a way that's highly analogous to the way we wrote the one-dimensional theorem. If your integrand is odd, and if your domain is symmetric, then our integral is 0. And again, massive convenience. I don't have to slice and dice a solid. I don't have to decide which way am I ordering my differentials. I don't have to think about bounds. I don't have to do antiderivatives. I don't have to worry about if the inside bounds are going to kind of muck up my outside integrand and if my life's going to turn bad, right? Because of ugly integrands, yeah.
So is L just some arbitrary line that you get to pick?
Yes. And you can apply this with any line as long as these conditions both work. Yeah, absolutely. So that is, you'll notice one of the warnings that I have down here. Both conditions have to apply. This is a delicate theorem, right? Everything has to line up. Close is not close enough. This warning here takes sort of two forms. Sometimes students will see a symmetric domain. It kind of geometrically presents itself most obviously sometimes. And they see that symmetric domain and they think, boom, integral 0 by symmetry. It's not. You got to check that the function is odd as well. And then the second warning, and again, very dangerous, and again, delicate theorem. You've got to be talking about the same line for both of these conditions. It is absolutely not okay to cite symmetry when the function's odd over one line and the domain is symmetric over a different line. That is not even close. No such theorem, no conclusion, nothing of the sort. Okay. All right, now let's talk about why this is true. I'm going to go back to what we had seen previously about single variable. There is a sort of an algebraic way to see this odd symmetry theorem, and it involves substitution, x equals negative u. Recall, substitutions are really just kind of the one-dimensional version of change of variables. And a quick side note, this is why I have this in the section on change of variables. Right? I could have done this earlier. I could have done this in 5.3. Right? But I like to connect it to change of variables because that's really arguably how you most powerfully, most elegantly prove this. But from an intuitive standpoint, I think it's much more satisfying to think of the integral in terms of Riemann sums. And what I'm going to do is I'm going to kind of group together these two, if you will, terms in my Riemann sum for this integral. And notice that the one of them is like this and the other one of them is like this. All right? Further note, these two widths are the same. Further note that because of the oddness, we get this minus sign right there. Okay. And then, once this equation is established, notice all it's saying is that this term in the Riemann sum and this term in the Riemann sum are negatives of each other, and when terms are negatives of each other, they cancel. Right, now again, I think the picture is pretty satisfying. Now again, I drew a graph here. You know, I kind of trash talk graphs a lot, I know, right? But in this case, yeah, it's kind of convenient and satisfying. Okay, so the same argument applies in two dimensions. And again, we could make a change of variables argument. If you want to walk yourself through this, go ahead, perfectly fine. I encourage that even. The big idea is to use the reflection itself as a change of variables function. And it follows through just like in the single variable case. But again, you don't need to worry about that. You're not responsible for that. Again, more intuitively satisfying. Let's think about this domain here. Notice I've drawn a wacky domain. This is my best attempt at drawing it to be symmetric, right? And notice that again, I can talk about this little piece, which corresponds to that, and this little piece here, which corresponds to that term, right? And again, they're the same size, and again, because of oddness, this value of the function is the negative of that value of the function, thus giving us that same minus sign. And of course, they're the same area as well. And so, as previously discussed, this term in the Riemann sum and this term in the Riemann sum, those are two separate terms in the Riemann sum, and they are negatives of each other, and so they cancel. I find this to be, very geometrically intuitive and satisfying. So that's why it works. And now let's get our hands dirty. Let's actually do one. So now I'm going to talk through all of the details on this one, arguably more than you need to actually say on an exam. Here we go. There's our integral we want to compute. Let's take a moment to recognize how scary that is. Right? Look at that integrand. Yikes. Right? I don't want to do it. I could. I don't want to. Okay, so, let's look at our domain. I'm going to draw a picture of our domain here, a little small picture. Over here, we'll start with this curve. Flashbacks to single variable calculus. Okay. And that ends up looking something kind of like this. And then we'll look at this curve, y equals -1. That one's easier. And what we're interested in as our domain is, again, the region bounded by these two curves, and that's this thing that I have in yellow right here. Everybody happy with that? Okay, so we look at the picture. Something kind of leaps off the page at us, and that is that this domain looks symmetric over the y-axis. Now, there is some issue as to how would I show that this is symmetric over the y-axis. I'm going to first make the observation that if I were to do a reflection through that plane, you look at a given point, and then I look at what its reflection would look like that. And here's a reflection over that line. All that happens when you do this reflection is, well, the y-coordinate stays the same. Nothing happens to y. But the x-coordinate at the reflected point is the negative of the original x-coordinate. And so I can write down this formula right here immediately, just, again, looking at the picture, right, interpreting the picture accordingly. Here's my formula for reflection. So, having done that, let's now ask, okay, how do I know this domain is symmetric? Well, look, I can plug in this reflection into that equation. That gives me this, which of course is that, which is the original equation. So, what I've shown here is that this blue curve, when you insert the reflection into the blue equation doesn't change. That means that this blue curve is its own reflection. So that blue curve is symmetric. That's satisfying? And then it follows, of course, then that the yellow region is symmetric. Okay. All right. Okie dokie. Let's see. Oh, where's my eraser? Why is my eraser not working? Is my pen dead? My pen is dead. I just charged this thing. Sorry, y'all. Give me a second. Let me get this thing plugged in so we can use it in a few minutes. Okay. Let's see here. Okay. That's charging. Yeah. Okay. Okay. So next thing. So we have a symmetric domain. Now we have to worry about our integrand. Here's our integrand. We'll look at that thing right there. How do I know if that integrand has odd symmetry? Quick reminder. How do we check odd symmetry? Here's the formula. Right, odd symmetry says that if you plug in the reflection, you should get a minus sign on the value of the function. Okay, let's just straight up do that. Here's our reflection right here. I'm going to take that formula for the reflection and just plug it directly in to that formula. As you can see right here, I'm just plugging in that reflection. So everywhere I see an x in this formula, I'm going to plug in negative x. Everywhere I see a y in this formula, I'm going to leave it as y because nothing happens to y in the reflection. And when you do that, our formula turns into this. You can see that reflection. You can see the minus sign on the x there, and the minus sign on the x there, and the minus sign on the x there. And then you got to play algebra games and ask yourself, okay, well, what happens when I have a minus sign that gets cubed? Well, I get a minus sign. What happens with this minus sign that's getting squared? It disappears in a puff of smoke. Cool. What happens with this minus sign? Ooh, I'm going to be taking sine of a negative of something. Think back to high school trig. This is one of what we call the symmetries of the sine function. And sine of negative something is just the negative of that. So this minus sign pops out. It cancels with that minus and makes this a plus. Everybody with me so far? All right, now again, why are we doing all this stuff? Why are we plugging in, et cetera, et cetera? What I need to know is whether the original value of the function, how does that compare with the value at the reflected point? I need to compare that expression with this expression. And what you're going to notice, look at each term. Oh my God, sure enough, they are negatives of each other. Yeah.
In this case, the reflection is really straightforward because you basically just like negate the
Yeah. I have several more examples coming. Yeah. I'm totally going to address that. Yeah. Anybody else? Is everybody happy? Okay, so we win. Game over. Victory. Let's see here, and again, cleaning up the mess. That's fine. I guess I don't really need that either. And we were looking at this integral. We have a symmetric domain and an odd integrand, and therefore the integral is equal to 0 by symmetry. Everybody happy? Yeah.
So when you have a problem in the domain that looks like something that might be symmetrical, should you always just go ahead and check that to see if it's also?
I'll at least eyeball it. Yeah. So for example, you could look up here and see, okay, well, that reflect. I'm going to get a minus sign on x, and I feel like I see a minus sign coming here, and I feel like I see nothing happening there, and I feel sine is odd, so I feel like a minus sign is going to show up for this factor as well. It's looking good. You still have to write it all down just to make sure, but yeah, I do think it's a good thing to scope out, right? And then if it's looking good, then actually write it out. Yeah. Yep. Okay. Again, a certain amount of work went into this, but again, consider the alternative, right? The alternative would be a nightmare of ugliness, and the nightmare of ugliness that we see here hasn't even yet factored in the fact that this curve has a quartic in it. And think about what happens if, that quartic is going to be your inside bounds. That means it's going to be in your outside integrand. Yikes. Right? Super ugly. Okay. So, let's see here. Oh, I forgot. I have this other stylus. I can use this. Better than my finger, at least. Okay, so here's a couple of comments about when you give a symmetry argument. I do need you to actually flesh that out. And for one thing, that's what this course is about. This course is about reasoning. I want to see a full reasoned argument as to how you claim symmetry. Okay, well, let's see those details. There are a lot of details, right? You got to actually give me those. So I'm documenting here for the purposes of this course exactly what you have to show me if you're going to use a symmetry argument. I need to see, and by the way, let's go through this list and observe as we go how I've done that in the above example. Let's see here, the line of symmetry, right there, y-axis. Let's see here, the formula for the reflection through that line of symmetry. Boom, there it is. Let's see here, I have observed correctly that the function is odd. See, I said so right there. Right, you gotta give me that. And I have also demonstrated that f is odd. And, again, that's where there's some algebra that's going to come in. And you got to show me that algebra. Sometimes you might argue that it's perfectly obvious that the function is odd. I would say if it is, in fact, perfectly obvious, then showing that it is odd will be easy. Right? So in all cases, I do want to see the actual algebra for that. Okay, last thing, you've got to tell me, let's see, I'm running out of colors again. I'll use dark green. You've got to observe and be correct that the domain is symmetric. What you're going to notice I have removed from this list, not included on this list. You don't have to prove that the domain is symmetric, right? So all this business that I did right here to try to persuade you that this domain is symmetric, that's, for your possible use, your possible, if you were having trouble seeing why this domain is symmetric, that's just to be persuasive to you. You don't have to give me on an exam any demonstration that the domain is symmetric. You have to state it, and you have to be correct about your statement. But you don't have to prove it. Is that cool? All right. Now, a second reason that I make you give me all of this, it relates to something that, when I was in college, I, on a few occasions, found myself in a circumstance where I was taking a test and I was working out a bunch of stuff and I ended with an integral and oh my gosh, there's only 10 seconds left on the exam. Oh my gosh, what am I going to do? Right, and then I just write equals 0 by symmetry, fold it up, hand it in. Cross the fingers. Right? And I'm going to say most of the time it didn't work, but a couple of times I scored. Right? And so, cool, good for me, lucky me. Now let's ask the necessary question: did I deserve those points? No. Oh, come on. No, I didn't. I didn't even hardly look at it. Right? I had not really understood what I'd written down. Right? So I do. I feel like I got away with something I shouldn't have gotten away with. Right? And so I'm going to make y'all actually earn your points. Right? No big deal. Again, here's a list of exactly what you have to show me, and this is kind of what I'm looking for, right? But make sure you go through this list and give me all 5 of these things. And that then makes a fully explained, fully flushed out symmetry argument. Okay. Everybody okay with that? Okay. All right. Now, I do have to give you a warning related to this. Let's see here. Let me clean up the mess. Related warning. And again, I've made this observation already, but the symmetry theorem that we're talking about here is very delicate. Right? There's a lot of ways that it can go wrong. You can have, for example, a highly symmetric domain, and yet your integrand, maybe 3 of the 4 terms have the oddness that they're supposed to have, but the other one doesn't. Right? And the answer there is that integrand is not odd. There is no symmetry argument to be made. And any argument about using symmetry in a situation where there is no symmetry argument is not progress toward a solution. That's progress toward a dead end. Right? So that's the really dangerous thing about symmetry arguments. Now, as much as I encourage you to use symmetry arguments, I'm a big fan. Do be really careful. Check very carefully, because if you put all your eggs into the basket of this integral is zero by symmetry, and if not only is your argument wrong, but if there is no symmetry argument to be made, nothing you've written is relevant to an actual solution, right? So very, very dangerous. It makes it practically impossible for me to give partial credit, and I hate when that happens. So again, I'm a big fan. I encourage you to use the argument, but be super careful because of that risk. Okay. All right. Now here's an example of a poorly written symmetry argument. Cringed as I was writing it. Here's the question. Right here is the hypothetical student's response. Right, and what the student writes here is true. This domain is symmetric. That function does have an odd symmetry. This integral is zero. There is a symmetry argument that shows that this integral is zero. Everything the student's written is true. There's just a couple of great big gaps in this argument, right? So again, it's been observed that the domain is symmetric. It has been observed that the function is odd. But this student has not said a word about the line of symmetry, and that's a real problem because this domain actually has four lines of symmetry, only one of which gives odd symmetry for the integrand. It is absolutely not clear what symmetry of this square the student is referencing. Yeah.
As you said, if there are multiple lines of symmetry, do we have to say all lines or just the one that you're referring to?
You only have you have to pick one. Yeah. Now, if there's multiple that would work, pick any of those that would work. You are not responsible for enumerating all of the lines that would have worked under what conditions, right? Just pick one and make sure it works for all the... Yeah, that's right. Yeah, no worries. Okay, likewise, the students made no reference to how a reflection works through that line, and which would, of course, be part of another thing the student didn't do, which is explain why this function is odd. Oddness is not obvious. Right? So this student has done 2 of the 5 required steps and would probably, if this were a 10-point question, this student would be getting 4 out of 10. Does that make sense? Again, keep in mind, it's not about answers. This class is just straight up not about answers. It's about reasoning, and the reasoning here is missing a lot of really important, non-trivial points. So, okay. Another example, and this is just for the example of it all. Here is a domain. I claim it looks like this. Y'all can think through. Oh, come on, that was terrible. Y'all can think through how this thing looks like that. And symmetric. Right? Now, in particular, it's only symmetric through one line. It's symmetric through that line right there, the line x plus y equals 0. And notice, here it is. I have noted the line of symmetry, right? That is the only one that works for this region. Okay. Now, again, you don't have to argue why you know it's symmetric. So all of this business right here is highly optional, and again, just there in case you're unable to persuade yourself on the basis of the picture, right? Just for your purposes. Okay. All right. Now, next, what's the formula for the reflection through that line? And I've written it down right here. And how in the world did I come up with that from this picture? Let me get rid of all these distractions. Where did I get that formula for reflection? Well, here's my line. There's my line. If I have some point, I want to reflect it, it's going to reflect about like that. Where would this formula come out of that picture? I think a really good trick for how to see this is to think about what I'm going to call a rectangular frame for that point. Right, let's draw the horizontal line that represents the x-coordinate of the point in question, and then a vertical little line to represent the vertical component. of that point. And the good news is it's really easy to see how a rectangular frame, that was weird, will reflect. Right? This horizontal line reflecting over a 45-degree line is going to reflect to be vertical. And this vertical thing is going to reflect to be horizontal. And so that green rectangular frame is going to reflect and turn into this blue rectangular frame. And so then you can just kind of keep track and be like, all right, well, whatever this x is that represents the first coordinate of my input point, that tells me how low, how far down to go. In other words, that will give me the negative of the output second coordinate because it's vertical. And thus, this minus x right here. Yes?
So in this case, we didn't actually solve for L as create an equation for it.
That's right. No, that's right. I mean, this L, I looked at the picture, right? The geometry presents itself, and I just have to see it geometrically that this is the line. And once I knew that this was the line, 45 degrees, kind of negative slope going through the origin. Take your favorite high school algebra method to find that equation. Yeah. Is that cool?
Yep.
Yeah. All right. Okay. So in general, how do you find formulas for reflection? They're all different. I've shown you a couple of different methods. If you're reflecting over a 45-degree line, this little business about rectangular frames is a nice little hack, right? I think it works well. I hope you'll find it useful. And then over here, we were reflecting through the y-axis, and again, you just kind of look at the picture, and the picture kind of should usually be pretty clear. If you want to make a symmetry argument over some arbitrarily, sort of weirdly angled line, that's harder. I don't anticipate that circumstance coming up. But if you're curious how to do that, just for outside of Math219 possible applications, I can show you how it involves some clever linear algebra. And come talk to me in my office. I'll be happy to walk you through it. Okay, shouldn't come up in Math219. Okay, let's see here. So now that I have that formula for reflection, I've got to actually plug in the reflection. See, here it is. Here's my reflection. I'm going to plug in my reflection. Let's see here. This was my integrand. Right? Plugging in the reflection into that, like so. Right? This being the F that I need to plug it into. It is a little bit easy to get confused when you're plugging this in. You have to keep in mind that when we write down x plus y to the 7th, blah, 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 this x means whatever your first input is. Notice that my first coordinate of my reflection is minus y, right? And thus, where there had been an x, we have minus y in the sort of the resulting transformed formula. So, careful with that. And then again, it's just a matter of keeping track of minus signs and the sort of multiplying things out, et cetera, et cetera. And as desired, we do get the minus sign. So this function's odd. 2 seconds. The function's odd. The domain was symmetric, as previously noted. All of my observations to be required to be made are in there. Integral 0 by symmetry, and I'm done. And I didn't have to worry about any corners or anything. Yeah.
Can you explain why y is your first variable for the reflection in the?
Yeah. Why is it minus y?
Yeah. Why is minus y your first variable that you wrote?
Yeah. So keep in mind, this is the function. Let's see here. This f right here. This thing right here is the formula I'm plugging into, and specifically what that means is f of, if I'm looking at f of x comma y, x is the first input that I put into this expression, right? Okay, if I want to know what I get when I plug in the reflection, right? So let me say that differently. What happens to this expression here? If I plug in the reflection, the first thing that goes in is not x here, right? The first thing that goes into this expression here apparently is minus y, right? This x up here is a placeholder saying, hey, whatever is the first coordinate that you're going to plug into this, put it right here, right? And so, well, the first thing that I'm plugging in to this expression is minus y. So this thing that's holding the place of where I should plug in minus y, I put in the minus y. Does that make sense?
I guess you just understand why it's as a negative y comma negative x.
Well, because that's what my formula is for my reflection, right?
Oh,
That's
you were just given that formula?
no, I derived this formula from this geometric argument over here.
Okay.
Yeah, so this whole business about rectangular frames and blah, blah, blah. So that's what justifies this, and this is what I'm plugging into my f function. Yeah.
Why are C2 and C3 reflections in themselves about L?
That's just a geometric appeal here. Let me draw a quick picture. Let's see here. So I have, there's my line, right? And let's ask what happens if I reflect, for example, C2. What happens if I reflect this line C2 over this purple line? And I claim that when it reflects over that purple line, it lands on top of itself.
Well, C2 is the line and L's the point.
Yeah. C2 is this line. Yeah, exactly. Yes.
Does the negative y, negative x at the top, that formula, does it have anything to do about the fact that you would have to reflect across y and then x? Like, is that the reason that there's a change of the order? Like, if you think about it,
But it's not. Very importantly, so I'm not reflecting over the y-axis and then the x-axis. I'm reflecting over this 45-degree line, and that's different, right? So if I reflect it across, imagine a point like over here, right? Here's the easiest way to see it. If I reflect across the y-axis and then the x-axis, altogether, I've done two reflections, which means my determinant would be positive. Here I'm doing one reflection. My determinant's negative. So you can't break. It's not as simple. You can't sort of just immediately say, this line is halfway in between these two, or something like that, right? You have to look specifically at the geometry of the specific reflection that you're interested in, and then use that geometry to derive the reflection formula. Yeah.
would we ever have a case where we can't use like rectangular frames?
Yeah, possibly. So there's the two different categories that I'm pushing here, right, are reflecting over 45-degree lines,
Or like the axes?
or the axes. And I don't want to say those are the only ones, but in all cases, it's either going to be something. In all cases, it's going to be a matter of looking at the geometry, right? And I'm not going to tie my hands any further than that. What I will promise is that I'm not going to ask you on an exam to reflect over a line that's 21 degrees north of west, right? That's too weird, and it's just not that it can't be done, but it's just I don't want to go off into that. Yeah, right. Okay, we need to move it along here. Okay, let's see here. Last example in 2 dimensions is a warning. Right? This is a landmine question. Students can totally screw this up. This is the catastrophe that I warned you about. That again, I can't give you credit for progress toward a solution if your solution doesn't work and it couldn't possibly even be fixed. Right? If you're making a symmetry argument when there is no symmetry argument, I got nothing. Right? So that's what's going on here. And the temptation is you look at this integrand, you see that odd exponent, and you think, hey, look at that, we've got an odd integrand here. And you do. That's the nasty thing. You do have an odd integrand. You look at this triangle, and you can draw a picture of that triangle. It's kind of like this, and hey, it is symmetric. And that's nice. The problem is that the domain is only symmetric over the y-axis. And the integrand is only odd over the x-axis. There is no line that makes both the domain and the integrand appropriately symmetric. There is no symmetry argument that could possibly be made here. So You really got to watch out for this kind of thing. That's why I'm a big believer. I mean, be extra careful that you do indeed check all 5 of the conditions, and that you check them, and I'll say double check them, just to make sure. Okay. Last thing, we're going to talk about the 3-dimensional version of this. It's exactly what you think it is. It's really exactly the same thing. If you have a plane in space, reflection, it's like looking in a mirror. Literally like looking at your reflection in a mirror. So again, how we write this down mathematically, we don't need to worry about that because it's the geometry, I think, is very clear. And when you have such a circumstance, right, you can talk about oddness. Talk about oddness as being the reflection giving you a minus sign, right? And you can likewise talk about what it means for a domain to be symmetric. And again, it's you can write this down formally, but don't worry about any of that. But it means exactly what you think it is. It means this domain is its own reflection, as you would expect and hope. The theorem looks exactly the same. Again, you have to check that the integrand is odd. Again, you have to check that the domain is symmetric. Again, you got to give me all 5 of the conditions, right, that I enumerated for double integrals. Again, be super duper careful that you check that both conditions apply, and that you check that you're using the same plane for both of them. And in that case, cool, integral 0. No spherical coordinates, no slicing and dicing, no nightmarish integrations. An easy example here, this integral is 0 by symmetry. You take away the symmetry of it all, and your best shot integrating over a unit ball might be in spherical coordinates. And you could totally do that. You can totally do this in spherical coordinates. But in spherical coordinates, X is full of trig, Y is full of trig, Z is full of trig, dV has a little trig in it. And so this is a pretty unhappy integral in spherical coordinates. Does that make sense? So we don't want to have to do that. The one little detail that I think I will go ahead and talk through, because I think I have a couple of minutes here. Where did I get this decision here to use the XY plane? Now this is not obvious. Why am I choosing the XY plane? In all the previous examples we've seen, the domain has motivated the choice of plane. Well, our domain is the unit ball. It's symmetric through infinitely many planes. It's awesome. Just massive symmetries as far as the eye can see. Okay, well then what we're going to do is we're actually going to use the integrand to motivate our plane. And I'm going to kind of reverse engineer the plane as follows. I look at this integrand and I know I'm going to have to plug in a reflection formula. I know that when I plug in that reflection formula, I'm going to need a minus sign to kind of show up. Where do I want that minus sign to be? Well, I could stick it on the X, but then it would just get squared and disappear, and I need it to stick around. Likewise with the Y, but I see this odd power on the Z. Right? So the first observation that I'm going to make here is that if I want an oddness to work out, I kind of feel like I'm going to need this to be my formula for my reflection. Now, this is a wish. This is a hope. Right? But that minus sign would just, that's exactly what I would need to make the calculation work. Next question, is this a reflection? And if this is a reflection, what's it a reflection through? And now here again, you have to think about the geometry. All that's happening in this reflection is that we're just kind of moving the Z coordinate, whatever it is going down to the negative of what it had been. And what is this a reflection through? Well, that's a reflection through the XY plane. And so the integrand motivates my hope for my reflection. My reflection is what motivates my choice of the plane of symmetry. Everything else is details. You got to go through and check the details. But again, nice punchline, no nasty integration, integrals equal to 0 by symmetry, and we walk away. Y'all have a great weekend. See you later. Hang out for a second if you would. Don't forget to stick around if I didn't get you on attendance yet.